So I want my presentation. I'm going to do it from now, and the paper I'll talk about today is showing one by Francesca and Molinari. I'm really impressed by algorithmic So all needless to say, there are lots of important constituents valued by algorithms, and examples range from network statements, developed to college management, and higher institutions. But these algorithms may have different levels of accuracy that vary a lot across subgroups of populations in ways that we don't want. For example, this 2016 Republican article that an algorithm used to decide who to fail has a false policy rate that's twice as high for Black evidence for conspiracy. And so for a fairness-minded agent, for example, a college admission committee, there are lots of policy-relevant questions that can be asked. One is whether we should just ban group identity altogether as the input to the algorithm. And just last year, the US Supreme Court ruled out things embraced in the college admission process. And so the answer to this question can really inform the debate on whether such policy is sensible. Another question of importance is whether for a given algorithm, there's a successful alternative in the sense that it's just as accurate but more fair. And this is really key to identify disparate impacts in a legal dispute where, for example, a college applicant files a complaint saying that they feel they're being discriminated against during the admission process. And the existence of such less discriminatory alternative provides evidence for the college applicant to prevail on that claim, whereas the lack thereof provides evidence for the college to justify that whatever admission procedure they're using is driven by pure efficiency. And again, for a given algorithm, another question of policy relevance is how far is it from the fairest possible algorithm? And for a fairness-minded agent who is willing to give up some level of accuracy to trade off for more fairness, for example, think of this imaginary college and affirmative action. The answer to this question can provide them with a tool to assess such trade-off that comparing two alternative algorithms in terms of their distance to the fairest point on the fairness accuracy frontier that I'll define later. Now, in principle, all of these are important questions that we want to address, but in practice, what we have access to is data from only 5 examples. And so in this paper, we're going to provide statistical inference tools to answer questions like this. And to do that, we're going to start with a theoretical framework proposed in this microtheory paper by Annie Liang, Yiqi Liu, Xiaoshen Lu, and Piu Yakumura. We're going to use their theoretical characterization of the fairness accuracy frontier. And what we do is to provide a statistical toolkit to first consistently estimate this theoretical frontier, including a couple of special points on the frontier, and then use this estimator to test policy relevant hypotheses like the ones that I just mentioned. And we also provide a consistent estimator for the difference between any algorithm and the fairest point on the frontier. Now, without further ado, let me get into the theoretical framework that we're going to work with, which is taken from this paper by Liang Lu and Yakumura, where we have a population of individuals. Think of them as college applicants. And they're described by an outcome variable y, which is some measure of potential college success. A binary group indicator g taking values in their rebel group. Think of it as race or socioeconomic status. And we also have access to a set of covariates, which can be standardized test scores, information on extracurriculars, and high school GPA. And for technical reasons, we're going to assume that these covariates are continuously distributed. If you have discrete covariates, you need to smooth them by adding a little bit of smooth points. Each college applicant will receive a binary decision 0-1 corresponding to whether admission is recommended. And there's an algorithm that maps from the space of covariate to a probability distribution over 0-1, corresponding to the probability of being admitted. And we're going to evaluate the performance of this algorithm using a loss function that takes in as inputs the decision and the observed label and maps to a real number. This can be your favorite loss function. Think of it as the 0-1 loss in the college admission example. And we're dividing group risk of an algorithm A associated with group G to be the expected loss for people coming from group G when the decision is assigned according to algorithm A. And the feasible and the algorithm designer or the college chooses an algorithm which in turn yields a risk allocation between the red group and the blue. And we're going to define a feasible sum of risks as the collection of all risk allocations for which there's an algorithm that maps to it. In other words, there's an algorithm that maps to each value in the support of the covariate to a proper probability between 0 and 1. And the key observation here is this feasible set can be shown to be a closed and convex setting R2. And this is formally proved in lemma A1 of Liu. So here's an example of a closed and convex setting R2. On the horizontal axis, we have the risk for the red people, and on the vertical axis, we have the risk for the blue people. And the feasible set has like smooth boundary, exactly because of our assumption that X has a continuous distribution. If it has a discrete component, then it's going to be a polygon R2 with flat faces, and that introduces difficulty deriving the asymptotic distribution that we'll not get into, but I'm happy to chat about that later. Now we're going to talk about preferences. We're going to say that for two risk allocations, E and E prime, is preferred over E prime if it's more accurate in the sense that the group specific risks in the pair E are way lower than those in E prime. And at the same time, it's fairer in the sense that the absolute gap between the group specific risks in the pair E is also way lower than that in the pair E prime, with at least one of these conditions. And the goal is to characterize the fairness accuracy frontier, defined as the collection of all risk allocations that are feasible, for which there doesn't exist another feasible risk allocation, such that it's strictly preferred over under the fairness accuracy preference relation developed. And it turns out that this frontier can be characterized by three special points on the boundary of a feasible set. The first special point is the feasible point that minimizes the risk for the red people. So that's the feasible point that's to the leftmost of the feasible set, because we have the risk for the blue people on the horizontal axis. And the second special point is the point that minimizes the risk for the blue people. And the last special point is this fairest point that's closest to the 45-degree line under our definition of fairness. So that's the point that minimizes the absolute gap between the group-specific risks. And here is a very nice theorem from Liu that characterizes the shape of the frontier, which says that the fairness accuracy frontier is going to be a lower boundary of the feasible set between the point R and B if the input space is what's so-called group balanced, in which case R and B will lie weakly on the opposite side of the 45-degree line. So in this picture here, this black curve connecting R and B is the fairness accuracy frontier. And on the other hand, if what we have is what's so-called R skewness, in which case both R and B lie above the 45-degree line, and this case is called R skew because even if you're doing what's best for the blue people, so even if you're at this point B here, the risk for the blue people is still higher than the risk for the red. And so in this case, the information contained in the covariates is sort of systematically favoring the red people, and that's why it's called R skew. What happens? Then the frontier will be the portion of the boundary connecting the point R. And in the last symmetric case, symmetric across the 45-degree line case, when we have B skewness, where R and B both lie below the 45-degree line, then the frontier is going to be the portion of the boundary connecting the point B and F. Okay. And so that's the theoretical framework that we're going to start with. And what we do is to take into data. And the key insight of our approach is to leverage the convexity of the feasible set. And because it's convex, it can be fully represented by the support function that I'll define later. And this will give us a closed form expression for the coordinates of these extreme points, including the points R and B and F that I just showed you. And we can formulate policy relevant hypotheses as restrictions on the support function, for which we can estimate using a two-stage estimator, where the first stage involves some infinite dimension uses parameter. And we're going to show that this estimator is asymptotically a Gaussian process, and this is an asymptotic result that we can leverage to formulate valid benefits. So now let me get into support function and how we use it to characterize the frontier. We're going to define the support function of the set in direction Q to be the improvement over the inner products between the direction Q and any element from the set. So take, for example, the direction 0, -1. Then this point B here is going to be the R2 of that inner product. And notice that the negative of the support function evaluated at that direction is going to give you the vertical coordinate of the point B. Next, we define the support set of the set in direction Q to be the intersection between the supporting hyperplane of that set in that direction intersected with the set itself. So if we again take 0, -1 to be the direction, then this pink horizontal line will be the supporting hyperplane of that set in that direction. And its intersection with the set itself is just going to be the point B. And notice that we can get the coordinates of any string points by evaluating the support function of the support set in appropriately chosen directions. So take again this direction 0, -1, for example. The support set in that direction will give you the point B. And if you further evaluate the support function of the point B in direction -1, 0, then that's going to give you the horizontal coordinate of the point B. And similarly, we can get the coordinates of the point R by evaluating the support function in appropriately chosen directions. So just to give you an idea of what the closed form expression for the support function of the support set looks like, here it is. It's essentially an expectation of a bunch of products of indicators of a nuisance parameter defined as the conditional expectation of the log times the group indicator divided by the group proportion. And this is infinite dimensional because we're assuming X has a continuous distribution. And this is an expression that you can take to data and estimate and characterize its asymptotic distribution. And I won't have time to go through the details of how we derive this expression, but those are in the paper, where we essentially look at the geometry of the random line segments whose expectation turns out to be the feasible set. So just a quick comment on learning the coordinates of the Ferris point F. It turns out that they are much harder to learn because they depend on the location of the feasible set relative to the 45-degree line. So in the paper, what we do is we first pre-test for the location of the feasible set, and then conditional on the results of that pre-test, derive closed form expression for the coordinates of the point F. Again, leveraging support function of another properly defined convex set. And the detail is in the paper. And we also have the chat online. So now let me get into how we express policy relevant hypotheses as restrictions on the support function. So for the first test of whether we should ban group identity, we're going to test the null that R and B lie weakly on the same side of the 45-degree line. And this is a policy relevant hypothesis because by the previous theorem from Liu and Algorithmic, noting the location of the point R and B relative to the 45-degree line reveals the shape of the frontier. And more importantly, it's going to tell us whether group identity should be banned because of the following result from Molinari, which says that if the covariance space is strictly group balanced, in which case the alternative is true, then using X only as input as opposed to using both X and the group identity information will uniformly worsen the frontier. So if we reject the null hypothesis here, then we have strong evidence against banning group identity. And this null hypothesis is sort of easy to formulate once we know the coordinates of R and B. Because whenever R and B lie on the same side of the 45-degree line, then the product of the difference of their two coordinates should be weakly greater than 0. And recall that we have closed form expressions for these coordinates by evaluating the support function in different directions. So that's our first test. And for our second test of whether there is a less discriminatory alternative to a given algorithm, let's call that given algorithm E star. We would like to test the null that there does not exist a fair or feasible point without sacrificing accuracy. An alternative corresponds to the existence of a less discriminatory alternative. And this is a policy relevant hypothesis because it gives us a tool to test for disparate impacts. And notice that the null hypothesis is essentially testing whether E star is on the frontier by the very definition of the frontier. And we're going to test this by leveraging the separating hyperplane theorem in the following way. We're going to first define another convex set C star, which collects all risk allocations regardless of whether they are feasible, such that they are weakly more accurate and weakly fairer than the given algorithm E star. So you can interpret this as the set of all improvements, regardless of whether they are feasible relative to E star. And its shape will depend on whether whether E star is above the 45-degree line or below the 45-degree line. So in these two panels, the green shaded area corresponds to the set E star. And observe that when E star is on the frontier, then you can draw a line through E star such that the green set C star and the feasible set lie on the opposite side of the 45-degree line. Whereas for the E star is off the frontier, then by definition, there's another feasible point that's weakly more accurate and weakly fairer, with at least one of them being stripped, such that there will be an intersection between the feasible set and this green set C star with a non-empty interior, in which case we cannot separate the green set from the feasible set. And we formally showed this in this proposition where we proved that there is an A-beta-only relationship between the fact that E star is on the frontier and the existence of a hyperplane that separates C star and the feasible set. And this separation can again be equivalently written in terms of the support function of the set C star and the support function of the feasible set. Now getting back to what we would like to test, we want to test the law that E star is on the frontier, and we can equivalently express this hypothesis through support function restrictions, for which we have a closed form expression for, and we can estimate and characterize its asymptotic distribution. Now getting to estimation and inference. What we essentially leverage is this asymptotic theory that we proved in the paper, where under a set of conditions, we show that the support function, the estimated support function converges to a Gaussian process uniformly in the directions that you choose. And to the estimator is formed by a two-stage process, where in the first stage you just estimate the infinite dimensional nuisance parameter. So yeah, and that concludes this talk. So we and take the data and test hypothesis of policy levels. That's it. Thank you. Thank you.
Do you have like numerical studies and that kind of stuff?
So yes, we're in the process of finishing an empirical application plus corresponding packages to implement the tests.
Okay.
This is a work in progress.